Okay, I carried over our notes from the other side. So for functions, when we have an even index, we learned on the other side that whatever's under the radical, which we call the radicand, must be greater than or equal to 0. That just means not negative. So that's just the mathematical way to write not I don't know, negative. I don't know if I have that spelled right. We'll pretend it's okay. No negative. Ha! See? Non-negative, no negative. And if it's odd index, we learned on the other side in the explanation box that any number can be put in for A. So when I see this problem, and remember this is on our test and our final, I put one down here that was most like the test. The minute I see the even index, I go, oh, I got to take whatever's under the radical and make it greater than or equal to 0. So set the radicand greater than or equal to 0. So what's the radicand? X minus 7. Greater than or equal to 0. Add 7, solve it like we learned on the second day of class when we were doing inequalities. So x is greater than or equal to 7. And remember, before we do the interval notation, because you don't want to make mistakes, just do a fast little graph. Greater than or equal to 7 looks like this. It must have an equal sign, and greater than goes right. So to do our interval notation, we do bracket 7, comma, infinity, parenthesis. And then our set builder notation. So this is interval. Let's label it just so. Notation. So you have the vocab down again. I know we went over it quite a few times. And this is set builder. Notation. So for set builder notation, all you do is write for all x such that, and then you take your answer and plug it in. So it's pretty easy, but you just have to make sure you have all the other pieces in it when you go to write it in ALEX. Then if they asked us, so that's our answer. Usually ALEX wants both. So this would be the answer using set builder notation, this would be the answer using interval notation. But like I said, they don't usually ask you to graph, but you should graph right after you find the answer, just so you make sure and put this in the correct order and use the correct symbols. Then we have an odd index for the next example, and we go, no work needed, love it. So here's our interval notation, and our set builder is x such that x is a real number. I think there's supposed to be an is there. X a real number. That just sounds weird. So odd index, no work. Just go straight to that. Even index, take what's under the radical and make it greater than or equal to 0. That means don't let what's under the radical be negative, because we learned that's a non-real number. So 15a was the one I found to be closest to the test. So I see it's an even index. Remember, when there's no number there, that means there's a 2. So the minute I see that it's an even index, I take the radicand, 3 minus x, and I say, oh, it can't be negative. So that means greater than or equal to 0. Subtract 3, subtract 3. Now you're going to have to dig some cobwebs out. What did we learn when the negative was in front of the x's with inequalities? Flip the symbol. Remember that? Because I'm going to have to divide by negative on the next step. So that turns into x is less than or equal to. So anytime you divide or multiply by a negative, we learned in the first chapter, the inequality flips. And then a negative divided by a negative is positive. So remember how I said draw a rough little graph first before you do your interval notation. So less than or equal to 3 looks like this. Negative infinities on the far end. So let's write both set builder and interval up here so that we have them both, because usually Alex wants them both. So the set builder notation would be for all x such that, and then you just plug the answer in. X is less than or equal to 3. So that would be our set builder notation for all x such that x is less than or equal to 3. For our interval notation, we go from left to right. So negative infinities first, 3 second, and 3 gets a bracket because of the equal sign. And remember, order matters, shape of the parentheses and brackets matter. So you keep it in the order of the number line, negative infinity first, 3 second, and 3 gets a bracket because of the equal. Negative infinity always gets a parenthesis. So that one is just like the one on the test and just like the one on the final. So make sure and highlight that. Cube root, I go, yes, I love this one. It doesn't take any work. So I just immediately write negative infinity to positive infinity. X can be anything, a fraction, a decimal, a positive, a negative, because the index is odd. So that's why. And then our set builder would be for all x such that x is a real number. And there we have it. C is kind of a special case. I like to put it on the homework just because it makes students think. But it's a little early, like to put a special case like this on a test. But remember how we were talking about x squared earlier? We said anything that's squared is always positive. So a positive plus a positive, isn't that always going to be positive? So this is g of x equals some positive number. Does everybody agree? Because a positive plus a positive will be some positive number. Well, this is how we make a positive greater than or equal to 0. We make it non-negative. So we can put anything we want for x. Put negative 100,000 in. This is still positive because negative 100,000 times negative 100,000 is positive. So nothing we put in for x could make this negative, because anytime we square a number, it's a positive, and we're adding it to a positive. So guess what? Even though it's an even index, because x is squared, we can put any x in we want. We can put negative 500 trillion in. When we square it, it's still going to be a positive. And so if nothing makes it negative, because remember that's our goal, that it's non-negative. So if nothing makes it negative, that means it's a free-for-all. Put whatever you want in, which would be for all x such that x is a real number. So that's a special case. Usually you don't see one like that, but I like to throw it in there to remind you, look at your problem closely. Just don't do like what I call it for students is I say, don't do mindless math and just automatically make it greater than or equal to 0. Look at the problem. X squared is positive always. And when you add it to another positive, you get the square root of some positive. So there's no way that I could find an x that wouldn't work. So that's why we can put any x in we want, because of the squared. So it would have to have a squared or a fourth power more than likely for you to write that. Okay, so let's see how this plays with a graph. So when we have a graph, we need to know what values to put in the table. So how we know what values is by doing what we just did up here. So we take what's under the radical and we make it greater than or equal to 0. Because this cannot be negative. It can be 0. I can do the square root of 0. It's 0, but it cannot be negative. So take what's under the radical, and remember this is an even index. That's why we're doing this. Now this one is almost like A that we did earlier. So negative x is greater than or equal to negative 5. And remember, this is negative 1 times x, so divide both by negative 1. Because we divided by a negative, flip the symbol. So x is less than or equal to positive 5. So write the domain in interval notation. The minute I see that, I go, oh, I need to first graph it. So less than or equal to, shades left. So just do a really rough graph just so you know the order that goes up here. So negative infinity first, 5 second. And there is so much domain and range in the next class. You really want to make sure you work hard on it in this class so you have it down before you go into the harder class. So less than or equal to, we flip the symbol because we divided by a negative, less than, shades left. So keeping it in the same order, we put it right there. So what does that say? That means as we pick our x column, 5 should be your first value. And then it says only pick numbers less than 5 or equal to 5. So how about 5, 4, 3, 2? Usually teachers want 5 points, so let's go ahead and do 5 points. Okay. So this says don't pick any x unless it's less than 5 or equal to 5. So I picked equal to 5, that's always a starting point, and then all numbers less than 5. So you're probably thinking, well, why can't I pick 6? Well, go up here to the original problem. 5 minus 6 is a negative. I don't know how to do the square root of a negative. It's not a real number. So that's why you have to do this step first to figure out what x's to use. Then you can move on to picking the numbers that work in your table. Okay, so 5 minus 5 would be square root of 0. When I put 5 in for x, square root of 0 is just 0. Then 5 minus 4, so put 4 in for x. Square root of 5 minus 4 is square root of 1, which is 1. Square root of, guess who's ready for dinner? 5 minus 3 is square root of 2. If you don't know what square root of 2 is, I believe it's 1.4. You just do second square root of 2. Sure enough, 1.4. And we can round because we're graphing this and we can't be any more exact than tenths on a graph. You know, if Alex asks you to round to hundreds, you round to whatever it says. But if it doesn't say, we just round to tenths, because how could we find 1.41 on the graph? You know, that's a little bit too specific. So next we do 2 up there. So 5 minus 2 square root would be the square root of 3, which I think is 1.7. Let's see. I'm just going to hit my up arrow and change that 2 to a 3. It's a little bit easier. And bingo, 1.7. And last but not least, put 1 in for x, so it'd be square root of 5 minus 1, which is the square root of 4, which is 2. And then I graph. 5, 0 would be here. 4, 1 would be here. 3, 1.4 would be a little less than 1.5. 2, 1.7 would be a little bit more than 1.5. And 1, 2. And so we can see our graph looks like this. So now the big question is, why don't I put an arrow on this end? Because remember, our x's have to be less than 5. This is where the x's are bigger than 5. but they can keep on going. We could have done 0.